Good afternoon, everyone, and thank you for joining our webinar with Hager on RCD applications. My name is Wiem Merki. I'm the marketing coordinator at Rexel. Our guests today are Paul Collins and Paul Chaffers, technical training managers at Hager. Please note this is a recorded webinar and will be available to watch on demand on our Rexel website. This webinar is CPD accredited and certificates will be sent directly from CPD, which can take up to 5 weeks. If you have any questions throughout the webinar, please feel free to pop them in the Q&A box, and we will answer them at the very end. Now passing over to Paul from Hager.
Thank you very much, Wim. Good afternoon, everybody. So I'm Paul Chaffers, and the other guy there is Paul Collins. As Wim said, we're the technical training managers up at Hager. Today's webinar is about RCD types and applications. Of course, it's bang up to date with the latest version of the wiring regulations. And both myself and Paul work on a number of committees that work towards drafting the regulations. So, you know, hopefully we can handle any of your questions today and give you a good insight into RCDs and the different types and why we use them. We're going to look at a number of topics. So I'll get Paul to just bring up the contents there, and we can have a look at what we're going to work through in the next half an hour or so. So different types of RCDs. In recent times, there's been a lot of discussion over this. So we're going to look at that in a bit of greater detail. Then we're going to look at how they operate. Paul's going to give us an insight into the different types and how they're made, what's inside them, basically. Then we'll look at the selection, different applications, different things you need to consider. And obviously, we're going to be talking about selectivity. Used to be discrimination in the old days. Selectivity covers one aspect of RCD selection, but we've also got this word coordination that we're going to be explaining and talking about that. And then lastly, we'll be looking at testing. There's also some other little bits we're going to throw in about the use of RCDs with solar PV and other micro generation. So yeah, away we go. So when we first talk about RCDs, many of us just use the term RCD as a common term, but typically we're quite often talking about RCCBs, which is the one there on the top left. That's the kind of RCD that you would have in a consumer unit, but it is an RCCB. So we don't tend to get too hung up on the different terminology. The wiring regulations would specify that you may need to provide additional protection by a 30 milliamp RCD, and it would be down to the designer to decide which was the best choice. Would it be to have an RCD that covered the whole circuit? Maybe it's just a part of the circuit. And that's where we see these different devices you can see on the screen there, from socket outlets to fuse connections, RCBOs. We've got portable plug-in RCDs. So lots and lots of different devices use the same sort of terminology. And then we start to see them creeping into other places as well. So with EV charging now, I think that in-cable control and protective device cable up there is what you tend to get supplied when you purchase a, you know, like a hybrid EV card. You get that simple charger that you can use from a ordinary socket outlet, and that's usually known as mode 2 charging. Mode 1 EV charging is just a simple cable with no controls in it, and that's sort of frowned upon because there's no protection there. So a mode 2 device will have some protective devices built into it. And then we can also see, sticking with EV charging, that we've got this term RDC-DD, which is residual direct current detecting device. So you really got to pay attention to the letters because they all sound very similar, but they've got specific tasks. And we're going to look at a little bit at EV charging later in the presentation. And then you can see the RCM there, the residual current monitor. That's a device that it does what it says on the tin, but it can also be built into other devices to be able to send a trip command if it needs to. So next slide is where we start to look at the types, and I've got the old Rex book here in front of me. So on page 156 we have this types of RCD regulation, and it says different types of RCD exist, and depending on the behavior and the presence of DC components and frequencies, the appropriate RCD shall be selected. Okay, and then it gives us the different types that you can see on the screen there. Now it makes that reference to the presence of DC and also to frequencies. Okay, so in years gone by, when we used to have old sort of tungsten filament lamps and heating elements and things like that, it was just purely AC running through our circuits, and we didn't see a lot of DC. But as time's moved on, we've got switch mode power controllers everywhere, lots of electronics, LED light fittings. There's a presence of DC on the waveform, and unfortunately an AC device, which is the sort of general purpose that we used to have in consumer units, they can be magnetized. So any of you guys that used to use the old Robin testers for your loop testing, it used to have a D-lock button on there, and what that was actually doing is taking DC from the batteries of the test instrument, and it was locking up the RCD to allow you to do a loop test. And obviously times have moved on, and we've got no trip technology now, and it uses a lower current, so it doesn't cause the device to trip under those testing conditions. But essentially, when we have presence of DC in an installation, it's doing the same thing, and a type AC device can be locked up. And for that reason, Amendment 2 of the wiring regulations sort of didn't put it through as a general purpose device anymore, and it gave us a note under this regulation that's on the screen, and the note reads that RCD type AC shall only be used to serve fixed equipment. So you can't use it for socket outlets. It's fixed equipment where it is known that the low currents contain no DC components. Okay, so pretty much type AC devices have been phased out. I just asked Paul a question. Paul, how long have we been selling type A devices in the Hager consumer units for now?
Type A devices have been around now there's the standard, certainly from Hager, for at least 5 years. Certainly when the 18th edition come out, or before actually, clearly because the level where we work with committees and stuff like that, we knew what was coming. So we knew that type ACs are going to be pretty much obsolete, to be fair. So we pretty much switched over around about 2018. So you wouldn't have bought a consumer unit with a type AC device in it since at least that time. So type A is our standard. Be a little bit careful when you're maybe just buying just an RCCB on its own from a wholesalers maybe, or from other sources where you might get some of these electrical products from, because obviously some old stock could exist. It was a really old stock now, of course, but some old stock could exist, and it's actually quite difficult to tell. They look, the picture on the left there, they actually look quite similar, don't they? Or they actually look bang on the same almost. So you have to really be clear with your magnifying glass, if you like, and actually look at the symbol on it or the letters on it, and that's how you would physically tell the difference. Obviously, some of that symbols and letters is even smaller, like on RCBOs, where it's only half that size. It's even smaller, so it is really difficult to tell. But there will be some indication on it that it is what type of RCD it is.
That's perfect, Paul. And of course, everybody's got a magnifying glass in their pocket these days in the form of a mobile phone. You can take a picture and just increase the picture to be able to see it. So it's fairly easy to do. But yeah, you've got to look out for those symbols. So as you can see, we've got a hierarchy of devices there. So AC is probably the worst because it can't deal with anything with a DC presence. Then we have a type A, which can do certain things, and it can detect and respond to faults in the presence of DC up to a level of 6 milliamps. Okay, and we're going to talk about that more later when we look at EV charging, but up to a point of 6 milliamps presence of DC, it will still work. Type F will take up to the presence of 10 milliamps, I believe, but it also is comfortable with some higher frequencies. And then we have type B, which is the best device, and it can do everything that the F and the A and the AC can do. And it's also able to, trip if the DC current gets too high. So that's the sort of king of RCDs there. But typically a type A is used throughout most equipment these days, and is suitable unless there is a very specific need for a type B. And we're starting to see that with some renewable technology and maybe some heat pumps and things like that. They may be specifying a type B device. So I think on the next slide, I'm going to hand over to you, Paul, to talk about the operation of RCDs.
Yep, so I get the cartoon slide. So this is very simplest form about how the RCDs function, of course. They work on kind of balance principles. So clearly in a healthy circuit, you know, what's the current supplied by the line conductor should be returned in the neutral conductor. And if we was to break open an RCD, we'll see some kind of magnetic toroid or something like that, where all the conductors pass through. They might go round it a few times as well, but essentially, if you look, they're all going in opposition. So if they're in opposition, the current flowing in that direction is exactly the same as the current flowing in the opposite direction. So the resulting magnetic force generated on this coil will be 0. Now, as soon as they're different, of course, which is when we've got some residual current means there's extra. Now, that extra current has only one place to go, really. It can only go to Earth. So the magnetic coil will detect some kind of induced voltage, of course, because there is some now excess current in one way rather than the other. And depending on that level of extra current, of course, it just then may or may not hit a threshold where it then sends it to the trip circuitry and actually then does its job, of course, trips the RCD. Now, we have two technologies of devices. Now, I'm actually not talking about type A's and things like that. So this is physically how they kind of how they work. And as manufacturers, we would call them voltage independent or voltage dependent. Now, that's quite clearly as it sounds, really. A voltage independent device, like this device on the left here, does not rely on a supply voltage for it to operate. So it's pretty much current operated. So as you can see the drawing there, and that's what I said about going around the coil a couple of times. If there is residual current such that the current in the line conductor, obviously then that's feeding earth fault current as well, is larger than the current in neutral conductor, the coil inside the product is sufficient to generate enough power to power itself in order to do the trip. Now, okay, to do that, the coil must be a certain size in there. So when we in the UK like to use actually one module devices, that's a bit of a challenge because obviously the physical coil inside there has to be a lot smaller. Now, if the physical coil is a lot smaller, the problem is with that, it doesn't generate enough power to actually operate the device, to internally do its workings, if you like. So it has to be always connected to a supply, i.e. voltage dependent. And what it is, the imbalance, if you like, from the coil is sensed and amplified in order to do the tripping. So you have to have a voltage on a voltage dependent device, mainly sort of single module units, in order to it to operate. Literally on the one on the left here, if we put you know, 10 volts through one side, operate it on 10 volts, as long as the right current is going through it, it would still work. Now, that's not to say you can use it at any voltage, of course, because the one thing that has to work on RCDs is you actually have to have a test button. So the test button, it will be voltage dependent. So operating this test button will depend on how much current imbalance is supplied through the test circuitry. So they will still have a minimum voltage for the supply, not necessarily because of the operation of the product itself, but for the test button circuitry to supply enough current through the product to actually do the tripping itself. Now, okay, we use mainly 30 milliamp RCDs or RCBOs, RCCBs, whichever one to call it. And there's a reason for that, actually. There's as a standard BS IEC, actually, strange code that, but it's an IEC 60479, which actually gives us some good information about the effects of electric current on a body. And we have this kind of graph here, which is the x-axis current going through a human body. Of course, this is an average human body, average build, average age, average, you know, health and things like that. So obviously it varies somewhat for elderly, young, etc. and this is the actual duration of current going through the body. Now, what that 479 did is divide up this parameters in zones. So we can see AC1 zone, AC2, AC3, and AC4 zones, which is broken up into different sections. So essentially then, if we could, the current going through the body was maintained in zone 1, AC1. You can see the current through the body up to 0.5 milliamp can be maintained pretty much indefinitely, and that would usually anyway, don't forget, on the average person, cause no harmful effects. However, going up into AC2, okay, so there could be some effects, okay, there should be some muscular contractions, okay, we can get to a point where your muscles contract and you have this no let go threshold as such, but essentially it shouldn't really cause any long-term harm if we could stay in zone AC2 here. Now you can see that goes all the way up to 200 milliamps, but very low duration now. And then if we cross into AC3, of course, once we cross this line here into from the green to the blue, then there's some trouble, of course. Okay, there's an increase likely of problems, cardiac arrest and things like that, immobilization, and all sorts of increasing problems. So if we look at the operating current of a 30 milliamp RCD, it sits in this zone. An 30 milliamp RCD could operate anywhere after half times that rating. So whatever RCD we've got, its operating zone is essentially somewhere between 50 and 100% of that value. So in a 30 milliamp RCD, the minimum operating current of that RCD is 15 milliamps. So it is somewhere on this dotted line here. So this will be the operating zone, if you like, of the 30 milliamp RCD. Not quite strictly true, actually, because when we check out 30 milliamp RCDs, as you know, I guess you guys would know, usually the operating time is around about 300 milliseconds. So I kind of needed to chop this off here, if you like. So it does keep us in zone AC2, because essentially this bit up here doesn't exist. Okay, and although in the standard it allows a 40 milliseconds disconnection time, so that's why this line goes pretty much flat lines out of here. In practice, of course, you know, as you guys would know, when you're doing 5 times test, or if you used to do 5 times test, you know, 40 milliseconds is quite a high number. It usually comes somewhere down about sort of 8, 9, 10 milliseconds even effects, the higher the current values. And this goes up to 10 amps even here, you can see. 10 amps going through a human body would probably not be possible, to be fair. The current through the human body will depend on where you're touching it, your contact, your skin resistance, whether your skin is dry, etc., how much path of your body it's passing through. So usually we're somewhere around about half an amp or so is possible for a human body. So that's why with the 30 milliamps one is the one that we use additional protection for against electrocution, I guess. Any 100 milliamps or more would obviously move this kind of yellow area to the right, okay, and that puts more of it into this unsafe zone. So we don't use 100 milliamps, or don't use anything more than 30 milliamps for additional protection against electric shock. Now I'm going to pass back to Paul for this one to talk about some regulations about where they're uses and different types of milliamps.
Thanks, Paul. Yeah, so I think most people are familiar with 30 milliamp devices as being used for additional protection, but of course there are devices out there with a smaller trigger rating. They may be specified for very special areas, medical maybe, I don't know, but 30 milliamp, if we don't go above that, it is recognised as providing additional protection, and that's really there for when we have a failure of basic protection, you know, a cable's damaged or whatever, and you know, and it exposes live parts, or it could be that there's a failure of fault protection there, you know, the ZS is too high for the circuit or whatever, so we're relying on the RCD element of the device. And it's also protection against carelessness by users. So, you know, cables that are in the walls and somebody's doing DIY and puts a nail through a cable or whatever, these devices are there. So they're like for life protection. So that additional protection is for life protection, really. So they're specified for a number of reasons in the regs, and we typically talk about additional protection for the purposes we've just spoken about, and we talk about fault protection where we might have a TT system, for example, where the you know, the impedance is too high due to the RF electrode to be able to meet your ZS values on your protective device, so you're using an RCD for fault protection. And we also specify RCDs for fire protection. There's an example there, regulation 705-4227. So below 30 milliamps, additional protection. Above 30 milliamps, we talk about using them for fault protection or for additional fire protection. So there's a number of reasons they may be installed, and you need to be able to get the grips with how you put them in a system to work and coordinate together. And on this webinar, we're gonna go into that. So sort of moving forward, I think we've got some images of equipment and different setup, and Paul's going to take you through this one.
Yeah, so this is about some issues and about what kind of fault currents or even load currents are possible for different types of equipment. Now, as Paul said earlier, no, AC devices are only now suitable for where there's a known fixed load and a known resistive supply, actually no presence of DC components. So let's say, for example, this was just a pure resistive water heater and a type AC device. Would that be suitable? Well, it would be suitable actually, because the load current will actually be a purely sinusoidal wave. Okay, there might be a little bit of distortion on it, of course, from noise and stuff, but essentially it's a pure sinusoidal wave. And then if there's any kind of faults, generally then any kind of fault current going through a person is a pure sinusoidal wave. So the type AC device in the consumer unit here would see that as a residual current now going through this person. There's an imbalance now, of course, through the product. So it will actually do its job and then trip within the required time, of course, and stop this poor chap here from being electrocuted. So type AC device there in that application is would have been perfectly suitable. But you know, as we know, less and less we're getting purely resistive loads. Even if we had an electronic timer on this, that would actually almost like muck up the kind of shape of this wave and make a type AC less and less suitable. So if we had more products with electronics inside, for example, this dishwasher with some timer controls and things like that, this is by no means obviously the circuitry within this product, it's just an example. So if the AC current was flowing towards the dishwasher, maybe, if there's any kind of internal faults in it, that could actually have a serious distortion of the actual wave flowing through the dishwasher. So that fault current then to the because it's fault into the case of the equipment, depends where it is inside, could literally be any shape. It could be a rectified DC shape, a pulsating DC shape like this one here. Further inside the product, of course, if it's possible to have a fault there, it could even be a DC type of fault. So that would be then obviously superimposed on the supply coming into the dishwasher. So there's all sorts of distortion now on that wave for that supply to the dishwasher. Now, if some poor chap, of course, is touching it because it's got a fault, okay, who knows what shape that wave will be. Okay, so this type AC device in the consumer unit is possibly blinded to this fault. So it's kind of magnetized that core, and as Paul said, almost a D-lock. You know, the old Robin D-lock function is going ahead here, and that's actually not allowing it to trip. It's locking this RCD up, and it's not going to trip. It's not going to detect any kind of residual current flowing to this poor chap here. And of course, even if someone wasn't touching the over here because it's got a fault on the product, this RCCB here feeds other circuits. So if there's any kind of fault on any of these other circuits, let's say this circuit here went to, I don't know, an outside socket to the lawnmower, and they made some mistake out there and accidentally touched the cable, then there's a serious problem because this device here is now locked up and it's not going to trip whatever or possibly won't trip whatever the fault was in any of this or any of the other circuits in this installation. So it's almost like there's no RCD now protection on this part of the consumer unit for these circuits. Now we can see, and actually we have seen, to be fair, equipment being supplied, just consumer equipment, that if you look inside the instructions, that says something about the type of RCD that should supply that equipment. We actually first saw it years ago on Bosch dishwasher, in fact, where this little piece of text was in the instruction leaflet. So use only a residual current of a circuit breaker which features this symbol. Now, the problem is, okay, most people won't understand what that symbol is, but okay, you can see that symbol represents, from a few slides ago, a type A RCD. So this is actually the instructions of this equipment. It is asking for a type A RCD. So if we was fitting something which we knew had that instruction in, we need to supply a type A RCD, not a type AC RCD. And if we're fitting it on to a piece of to a circuit, or adding it to a circuit, or replacing this piece of equipment, of course, you know, it might have been fed, this boiler, I guess it is, might have been fed from a standard, you know, 13 amp fuse connection unit, because in those days it was fine. It was backed up by an RCD in the consumer unit from the circuits. Now this instruction is requiring this type A RCD. What do we do? So could we simply change the fuse connection unit there, instead of from just a fuse spur, to a fuse connection unit with an RCD in it that may be a type A? Now, if we could do that, that kind of ticks the box for the boiler manufacturer here. However, okay, it might cause a problem, because any current going to the boiler here in this example clearly has got to go through this circuit breaker, and clearly it's got to go through this RCCB. So, you know, if there is this thought in the wave at all, that could cause a problem to the RCD here, which may mean that there's no RCD protection on the socket outlets in this circuit. May also mean, of course, there's no RCD protection on the other circuits of this parts of the consumer unit. In 7671, it gives you these kind of weird drawings. Actually, it's actually in section 5.3 and annex 53, actually, where we see lots of different drawings and possible load types. Now, not too worried about the actual electronic drawings in the first column here, but you can see what possible shapes of both load current and fault current are. Now, you can see the first couple here, they essentially change direction. They go positive and negative. So maybe an AC is still suitable there, but the ones further down this table, and actually I've just clipped a bit off of this table, so there is more down there. If you wanted to check out this drawing in Annex 53, you can see some of them, a lot of them in fact, don't change direction. So the type of RCD suitable for this application, you can see AC is now missing, and it can only be now A, F, or B. So it is really a consideration where we're adding certainly fixed equipment to an electrical installation that we think has electronics inside it, or is likely to have electronics inside it. So would require a type A RCD at least, and not a type AC. Now, I think I'm passing you back to Paul now, for we're talking about some text from 7671 again. Over to you, Paul.
Okay, thanks, Paul. Yeah, so this is what I was talking about earlier, the regulation that gives us our different types of RCDs. And what we're going to look at is this note here. So I spoke about this earlier about the 6 milliamps, but it clearly shows us there that, you know, the device can still operate up to that level of DC presence, okay, flowing through it. So this is particularly important when we look at EV charging. So I'll just get Paul to flick the slide. We've got on the next slide, we've got EV charge point regulations 722.
Sorry, Paul, do you want me to flip the slide? So, sorry for you guys online, so it's only one of us can drive the slide. So yes. The point of this bit, okay, in this text of the regulation, Paul, it's not about the 6 milliamps is nothing to do with tripping at 6 milliamps, isn't it? It's about not affecting its operation. That's the problem here, isn't it? Yeah, so yeah. I'll let you go with this one, sorry.
Yeah, no problem. Yeah, so the EV section 722 for electric vehicle charging installations, first of all, the RCD is the regulation is very clear that it needs to disconnect all live conductors. So that's the line and the neutral conductor. So that's very clear. Then we also have this regulation that says unless you're using the protective measure of electrical separation, which is doubtful because electrical separation is, you know, quite an expense to get an isolating transformer, can only be used for one charge point. There's a load of stipulations with it. There's also possibly losses from the the workings of it. So quite often we don't see that being adopted, but it's quite possible you can use that as a protective measure, of course. So unless you're using electrical separation, each charge point shall be protected individually by its own 30 milliamp RCD of type A, F or B. So that part of it is really clear. The bit that we've got missing there from the text is it says that you can use a type A or an F if it's in conjunction with an RDCDD, okay, and that's the device we spoke about earlier. Now the RDCDD, what that's doing is that's preventing too much DC going back through the device. So most of those RDCDDs in the charge points will be set around 5 milliamps, maybe 5.5 milliamps. So if the circuit starts to see any more than that, the RDCDD cuts the charge point off, preventing the type A RCD from being compromised. Okay, so it won't be blinded and it'll still be operational. As soon as the level of DC settles down, the charging recommences and it carries on. So the two are working together. Okay, so there's a few things there that have changed. Amendment 2 brought in this individual wording. Now the individual wording is to try and prevent you from putting a charge point on, say, a split load board with a number of other circuits. So it's the intention is that you supply this by its own RCD. So I'll just get Paul to flick the slide over there to the next one. So this is what we're looking at here. We've got that RCD, that type A. It's built in this instance. It's built into the charge point. We've got a number of considerations. Do we need an RCD on the final circuit? That's going to depend on how the cable's wired, of course. If it's surface mounted, we may not need additional protection. If it's a TT system, we may need fault protection, but it may not need to be a 30 milliamp device. You know, so there's a number of things you need to think about. But as Paul's already said, if it was a type AC device, it would be no good, because the charge point, we know it's got this characteristics of DC. We know it can let through a level of DC before the RDCDD kicks in. A type AC device would be compromised. So therefore, we would need to at least match the types. We'd have to have a type A feeding a type A. But there's so many considerations, and if you're doing electric vehicle charging, you really do need to understand all of this, because it can be quite expensive if you're putting in a type B device for a particular application and you're in series with another RCD that would also have to be a type B device. So you know, really do need to consider this, and sometimes it's worthwhile sort of designing the wiring system to get round using an RCD at the consumer unit or the distribution board, and maybe have it in the final position of the charging point. But you know, there's so many considerations there that we've just run through. You just really need to be aware of them all. So that kind of brings us on to selectivity and coordination. Now this Paul's going to explain the selectivity part of the devices to do with residual current and how they operate, but this beamer guide here, it does give you some guidance on how you should connect. And what we've been talking about is this coordination. And if you look at the images at the bottom there, you can see you've got a type A device. Okay, upstream from that, we've now got an RCD that's time delayed, but it's also type A. So like I say, Paul's going to explain the time delay part, but it's also type A, so it's equal to it. But where we move along to a type B or an F, we cannot now feed them from that type A. So you would almost kind of like need to use a Henley block arrangement, feeding those devices and those applications, so it wasn't running through your type A that may be in the consumer unit. So you really do need to consider, if you get a heat pump or you've got a EV charger that's calling for a type B device, this device cannot be fed by another RCD that's not as great as the type B. And putting two type Bs in series is going to add significant cost to the project. So really pay attention to that sort of setup. So I'll hand over to Paul now to talk you through the selectivity requirements.
Yeah, so you also really need to consider the wiring type, won't you, for this bit here as well. So, you know, as you said, Paul, you really want to, you know, design out the RCD requirement for this circuit if possible, wouldn't you? So selectivity, except for a couple of occasions actually, selectivity isn't a requirement of 7671. The words, haven't got my book in front of me, but the word something about it says where selectivity is required, you should provide selectivity as a design of electrical installation. But clearly selectivity would be a good thing to provide if it's easily done. And with RCDs, it's actually relatively easy done actually. So if you see my drawing here, so I've got kind of trying to show 4 levels of RCDs in series. So this is my supplier over in the top right here. So I'm coming through some multi-case circuit breaker that's got an RCD attachment. So let's say this is a, I don't know, TT installation, maybe in a, I don't know, some kind of, I don't know, agriculture or wherever it is, doesn't matter where it is, but a TT installation where I need RCDs for fault protection. And then I've got through the sub-distribution, I've got one here and then one here. This is just a quick drawing from the 7671 actually. So device here and then 2 sub-devices here, maybe more, etc. So the golden rule for providing selectivity of RCDs is to provide time delay. Okay, now I'm going to come on to time delay in a minute, but and a ratio of at least 3:1 for the milliamp. So when I put these devices in here, let's say this is a required RCD at the bottom here for additional protection. So this is likely to be the end one, 30 milliamps, and maybe device 22 here is also 30 milliamps, and it could be a 23, 24, etc. So 30 milliamp devices for the end equipment. So if I need to provide an RCD feed in this distribution board, okay, what type of RCD would this be? So, well, the golden rule here is 3:1. So 30 milliamps times 3 is 90 milliamps. Of course, we don't make 90 milliamps. The nearest one we can get after that is 100 milliamps, and time delayed. So time delayed is an S type. If to identify the product, if you haven't got it from the packaging as such, there'll be a small square box on the front of the product and there'll be an S written inside it, and that actually S stands for selectivity or selective. So it's actually telling you it's provide a selectivity type of device. So if you get a fault here, as I'm trying to show, this one will disconnect. This is time delayed. Okay, so this will actually wait for this chap here to clear the fault. Clearly, if something wrong here with the fault, this would operate as well. So let's say the fault was 30 milliamps. Okay, actually, if it's 30 milliamps, you won't need a time delay because this is not going to operate lower than 50 milliamps. But if the fault here was 100 milliamps, say, this would then be in its operating zone. So we time delay it, so it waits for this chap to clear the fault. Once the fault's gone, of course, this can still happily supply all the other circuits, maybe from that final distribution board. Now, if we, for whatever reason, need an RCD upstream of that, normally we'd have some kind of MCCB stroke RCD add-on or modular RCD functions from that lot. If you remember from the first slide, you might have seen it here, RCD attachments, quite commonly for MCCBs, or we can use the components of an RCD, a toroid detector, and a trip device that goes inside. It's the same thing essentially. It'll provide you with an RCD that will trip under residual current. Now, once we get to this type of level, we usually have adjustment settings. So here's the magnified version of the adjustment screws on this RCD add-on block for this MCCB. Now, the adjustment options usually are time and current. So we have adjustment of current at the top here, I delta N in amps. And at the moment it's pointing to 30 milliamps, and it can go all the way around to 6 amps. So that gives us the current adjustment. And the bottom dial here, you can see a time adjustment, delta T in seconds. So either instantaneously, so no time delay, or we've got 60 milliseconds, etc., all the way up to a 1 second time delay. So if we follow the rule then, so 3:1, 100 milliamps. So a good choice for this one will be 300 milliamps. You could wind it round all the way, of course, but if you wind it all the way, it's got to be at least 3:1. But if we wind it more than 300 milliamps, then that gives us a problem for the next one upstream. We've got to make that even bigger. So we don't need to go more than we need to. So 300 milliamps, we'd set that dial to, here, 300 milliamps. So it will move around to point towards the little tiny flat plates, flat screw in there, switch that round to 0.3. That makes that now 300 milliamps. Now I'm suggesting we change the time delay to half a second. Now I'm going to show you why that is in a minute. It's a table from the RCD standard. There used to be this very handy table in Appendix 3 of 7671, but for different reasons now that's been removed. So the table would have said, and I'll show you the table in a minute, the maximum operating time for a time delayed RCD is 500 milliseconds. So if that's the maximum operating time, if we turn this chap here to the delayed time, i.e. the wait time of 500 milliseconds, then clearly this device would have operated while this time delay is still clocking along. Yeah, this time delay only expires at 500 milliseconds, in which case then it starts to trip, in case this one hasn't. So that's quite how you provide selectivity on 3 levels. But then what about up here? Same thing, 3 to 1. So 3 times 300 milliamps. Okay, so we now got 1 amp maybe. We've got the nearest one above. Okay, but where do we get the time delay for this product from? It isn't in the standard. It isn't in 7671. Okay, the only place we can get the operating time of this product here is from the manufacturer. So you'd have had to get in touch with Hager or whatever manufacturer you choose. What is the operating time of this device with these settings? It's not 500 milliamps, 500 milliseconds, of course. That's the delay time. It's going to delay for 500 milliseconds, and then it's got to do its job and operate. Now, it's something like 800 milliseconds, actually, from our data. So 800 milliseconds is the maximum operating time. So we need to turn this one all the way around to at least 800 milliseconds. Of course, we don't have an 800 millisecond setting, so we turn it around to at least a second. So that's clearly how you provide RCD protection and selectivity in multi-stage. So it's easy here, not too bad here. Gets a little bit more complicated here, but it's still relatively easy as long as you've got the information. And this is the table actually from the standards I was just talking about there. So more or less, this table 1 from the standard for 61008 for RCCBs would have been the table in Appendix 3, and this told us that for 30 milliamp RCDs, which is this column here, the actual milliamp I delta N column, less than 30 milliamps, greater than 30 milliamps, general purpose, i.e. instantaneous operation, or S-type or time delayed. And this gives us the operating characteristics depend on how much residual current we put through them. So this is the table that told us that for 30 milliamp RCD, when we test it at 1 times I delta N, if you remember, they trip within 300 milliseconds, or if you test them at 5 times I delta N, 150 milliamps, they trip within 0.04 of a second. Unfortunately, I'm going to apologise here again. Anyone remembers our RCDs we brought out when the 18th edition Rigi come out, when we brought out our new RCCB to cope with 100 milliamps for the overload protection of the consumer unit. Okay, we actually coordinated them for 250 milliamps because it was allowed by the standard. So apologies again for that. If that caused anyone any problems, we have corrected that obviously years ago now. So 150 milliamps, they trip within 0.04 of a second. Now you can see the actual title of this table though is limit values of break times for alternating and residual current. So basically when you put an alternating current through this device, these are the trip time, and it's relevant for both type A and type AC RCCBs. Now, when we brought out type A RCDs, testing become a bit more confusing. Sorry. Oh, sorry. What I missed off is the time delayed devices here. This is the 130 milliseconds minimum trip time and 500 milliseconds maximum trip time. So if you remember from that slide before, for the S-type device, operating time of 500 milliseconds, and that's why we set the delay time on the one above for that 500 milliseconds. Now, so when type A devices become the common device, if you like, what we was doing there is changing our setting of our machine to the type A setting. And what that was doing, that was injecting a pulsating residual current. Now, pulsating residual current was relevant to table 2 in the standard. Now, table 2 in the standard gives us, or give us similar values, but actually slightly different. So What the table 2 is requiring, if we're going to inject a pulsating residual current for a 30 milliamp device to trip within 300 milliseconds, we should have been injecting 1.4 times its current rating. To trip it in 40 milliseconds, we should be injecting 350 milliamps. Now, we was injecting lower values than that and still checking against those times. So when we had lots of discussions with this at committee level, we kind of got to the realization that we wasn't really testing RCDs correctly, because we was putting a half-wave test or current test through the RCCB, but we was actually checking against these times and these values, which was not strictly correct. Wasn't really a problem because the value was low. So when we set our machine to 5 times 30 milliamp, which is 150 milliamps, we was checking to make sure it disconnects within 0.04 of a second, but the actual time by the standard should have been 350 milliamps. So if we could pass 150 milliamps and it tripped at 0.04, sorry, if we applied 350 milliamps, clearly that would have been a bit quicker. So we wasn't worried about, you know, then lots of RCDs that haven't been tested correctly and might be faulty as such, because the current value we was actually injecting into the RCDs was low. Now, because of all this confusion, what we did was tidied up and made the RCD testing considerably easier. So we said that in Amendment 2, we introduced these notes about testing RCDs. So regardless of the RCD type, doesn't matter if it's type AC, A, F or B, we would check the effectiveness of that RCD to be verified if it disconnects within these times. So when an AC test is applied, so we won't set our machines any longer to A, just to do the standard test. We'll set our machines to AC and we'll inject an AC. Okay, so for general type, as long as it trips within 300 milliseconds, that's fine. We'll deem the effectiveness to be verified. And if it's for a delay type, between 130 and 500 milliseconds, again, we deemed it to be acceptable. So that's why we made the testing a lot simpler for RCDs. And that must be a lot of help for some of you guys, especially if you got, I don't know, you can have TP&N boards wrapped full of RCBOs these days. And the RCD testing would have taken quite a bit of time. And obviously now with this new testing regime, you can do it in a lot quicker. So we're moving towards the end of the seminar, but there's one more really important topic that's come about recently, and that's to do with actually which way the current goes through the RCDs. So we've had a lot of debate about this, Paul, haven't we?
That's right, Paul. Yeah, we have. I first started looking at it when we brought out this new prosumers section in the regs, part 8. And this regulation that you can see there, the selection and erection of overcurrent protected devices shall take account of all possible directions of current flow and polarity. So polarity is something we've been used to over the years, talking about correct polarity. But current flow direction, when we started looking at this, it's become a bit of a problem really for installers out there, where lots of installers making errors in installing micro generators to devices that were known as unidirection devices. So a unidirectional, the current can only go in one way. For a device to be able to accept the current in both directions, it needs to be a bidirectional device. So many of these RCBOs, all different manufacturers, if they are marked in and out or line and loads, then the current must only flow in that direction. So if you put solar PV into out terminal, then you're doing it incorrectly, and that can damage the device, and that can sort of stop it working. So what do they need to look for, Paul, in that device? You know, it's quite clearly marked, isn't it, on our devices?
Look at the device, basically. Look at anyone's device. So probably a little bit difficult to see. You might just about pick up line and maybe load and out written on the product there. Okay, it will be with the instruction leaflet that comes with it, but clearly if you're doing any kind of ERCRs, you might not have access to that. So literally written on the product, you'll see line, load, or in and out written on the product. And if you see that written on the product, it is a unidirectional device. If you don't see that written on the product, by default, it is a bi-directional device. So, you know, we do have alternative products that are not shown on this presentation actually, but are bi-directional devices. They don't have in-out line load written on them. Now, that has come to mind recently, but the other thing that's come to mind recently, hasn't it, Paul, is about the neutral switching. Again, as the small joint on the product identifies that.
Yeah,
Most RCBOs don't switch to neutral.
that's not really a new requirement. So the problem with the wiring regs is people read it in isolated sections. So they go to, like, say that, for example, they're doing solar PV, they go to section 712 and they look at the requirements for solar PV, but they forget to look in the general requirements. Within chapter 55, we have a section for other equipment. So within that section, it will tell us what we need to do if we're connecting a generator in parallel. Now, if we're using a cable to feed that generator, so let's say a microgeneration inverter, a PV inverter, if we want to provide additional protection for that cable, let's say the cable's buried in the wall and we want additional protection, then in section 55, it tells us that chapter 55, it tells us that we need to also switch the neutral. And a lot of the existing single mod sort of RCBOs out there don't switch the neutral, as you can quite clearly see there on the left-hand drawing. So you'd be looking for a drawing similar to the one on the right there, wouldn't you, Paul?
You would, yeah. So clearly you can see on the product, again, it would be described as, might be described as single pole switch neutral in catalogs or information like that. Or we see these kind of two contacts, one in the neutral. You can see clearly the difference there. There's no, on the neutral side here, there's no kind of contact break, if you like, on the neutral side of that product, where there is on this product. So any product with this drawing on clearly would be a switched neutral type product. Yeah,
perfect. So it's a good one to point out, because there's a lot of systems out there installed, a lot of guys doing EICRs. If they come across this situation, they've got to be able to make a decision. And we know that Beamer have released a document recently all about this subject, so please feel free to go and have a look. It's all explained what the issues are in full. We've given you a snapshot of that today.
yeah, and all those Beamer there's several Beamer documents actually. They're always worth. I keep telling people every time I do presentations, there's several Beamer docs. They're all free. Okay, you can get them all from the Beamer website, or just Google Beamer technical documents. You'll find it. And there's all sorts of other, well, we think very interesting Beamer documents, obviously on the guide, and giving you lots of useful technical information. Yeah. I think we've come to pretty much the end there, haven't we? So. We've
come to the end. What we didn't do is this time we didn't include the slide to advertise the next webinar. So we will be back. We're back on the 10th of November, and we're going to be looking at consumer unit design. So we're going to take all the regulations that you need to consider. So we'll include some things we haven't spoke today, but like unwanted operation of RCDs. We'll also look at the requirements for SBDs, the requirements for AFDDs. We'll look at configurations. Is split load okay? Do we want to go RCBO route? We're going to have a real good discussion on consumer units on the 10th of November. And then I think we're over to William for some questions.
Thank you both for this great presentation. So we have a few questions on the line. I'll start with this one. For coordination in modular industry, if we have a type A RCBO and an MDU feeding various consumer units in each of the modular bays, would a type A RCCB be required inside that consumer unit?
I'll take that one. I think I understand that. So when you've got RCDs in series, the one upstream needs to be at least as good as, at least, can you remember that hierarchy? There's A, C, A, F, B. Obviously they get better as you go down that line. So you wouldn't have a worse one upstream from a better one as such. You should not have an AC upstream from an A. There are times when you can actually. So this is a general requirement. AC shouldn't be upstream from an A. So if there was all A's, that's fine. Yeah.
Just to add further to that, Paul, because the question could have been taken in two ways. It might be asking, is there a requirement to have one upstream? And of course, that would depend on the the application, the wiring system, the earthing system. So if there's no requirement for RCD protection, it's quite possible that you could not have one upstream and just have it at your final circuits. So it's really difficult when we're on these calls to get the question and try and put it into some sort of content. So, you know, as Paul said, if you've got them upstream, they've got to be as equal, but you may be able to design your way around that depending on earthing systems and wiring types.
Thank you both. Another question. Can you briefly explain how some manufacturers have now got rid of an earth flying lead on their RCBOs?
So I'll take this one. So the functional earth of the RCBOs cause lots of problems. I mean, it's there, if you remember there, because they're voltage dependent. It was there for the extremely rare occasion whereby if you lost the neutral fly lead, for example, you could then still have a supply to the RCBO. And then because it didn't have a neutral connection, it had a separate earth connection as a kind of a double safety, if you like. So there was a double fail safe application for that white, or actually cream, it was intended to be functional earth. Now, two faults would have to happen for the functional earth to have any kind of use, i.e. you lose your neutral supply and simultaneously you have an earth fault. Okay, so the chances of one of those things happening are slim, of course. The chances of both of those things simultaneously happen is infinitesimally small. And the RC and the functional earth caused lots of problems, i.e. you can't test with it connected. It's a small cable, it's awkward for it to connect into the same earth terminal as the CPC for that circuit. So most manufacturers like us has looked at it as a kind of a risk, if you like, system, and remove the functional earth, as I said, because you need two faults simultaneously to happen at the same time. 7671 doesn't really concern ourselves with two faults simultaneously, only really one fault. Only for IT systems do we worry about second faults. So we've decided, because it was a problem for installers to connect and test, we decided, and the same as other manufacturers have on balance, to remove it. Don't know if that helped answer that question, hopefully.
Thank you, Paul. And just to end with this question, does Hager make the DP RCBO, i.e. neutral switch, in one mode units?
Well, funny we should say that. Literally, I think within the next week or so, we will be launching a single module RCBO, very similar to the in size to the RCBOs we have in our consumer units today, that will be double pole. So it'll be double pole. Well, I say double pole, that's probably it's single pole and switched neutral, means it's active on the line side, but it does switch to neutral as well. So the correct term for that, of course, is single pole switch neutral, but double pole would do, I guess. So it does, yes, switch to neutral. So we will be launching very, very, very shortly. We had confirmation this week, actually, that they are suitable to use in our consumer units. We've had them for a while, to be fair. But with a company like ours, what we do is undergo really, really rigorous testing. So a double pole or single pole switch neutral RCBO generates more heat than a single pole RCBO. So we have to be very clear with our certification and our laboratory that this extra heat generated is okay for generating that extra heat in our consumer unit. And we won't sell a consumer unit with these devices inside until we've verified it by quite extensive testing. You know, it's not as simple as, okay, you know, we've had a double switch neutral RCBO for probably 5 years, so we could have easily said, you know, a few years ago, yeah, okay, we've got one, just put it in a consumer unit. We won't do that. Okay, we're not a manufacturer to do that. We go through very, very rigorous testing to make sure it passes all the required tests by the standard. So yes, we have one now. So I could have said just yes earlier on, I know, but I wanted to give a bit more information about, you know, about the testing requirements. Hope that's okay.
Just to add that, Paul, that device will also be bi-directional, correct?
And it's bi-directional. Well done. Yeah, I forgot about that. Thank you. Yes, it's bi-directional. So it is not marked in-out line load. You can tell by that inference it's bi-directional.
Perfect.
Perfect. Thank you both.
Okay.
So we come to the end of the webinar. If anyone has more questions, please feel free to send them at marketing@rexel.co.uk, and we can respond and put you in touch with Paul for any further inquiries or any assistance you need in your projects. So thank you for joining us today, and see you soon, hopefully in the next webinar.
Thank you.
Thank you. Bye-bye.